Every 300,000 or so years on average, Earth's magnetic fields do something crazy. They change polarity, meaning what was once the north magnetic pole becomes the south magnetic pole, and vice versa. But why does this happen? Well, it turns out that Earth's magnetic field is caused by its iron core, and this core is rotating. Now, the process by which the magnetic field is generated essentially involves rotations of magnetic moments. And what happens is there's a magnetic field that is continually created, but it's also continually varying, meaning at any given instant, the magnetic poles are always shifting. But incredibly, over time, these shifts can cause balances to go off, and we can completely shift polarity. When you're in the space station in orbit around the Earth, is there gravity? Why are you floating? Well, there is gravity, and we know there has to be because if there was no gravity, the Earth would simply zoom away from us and we would be left all alone in outer space because the Earth is going hundreds of thousands of miles per hour. But then why isn't it like when we're on Earth on the ground? Well, when you're orbiting an object like the Earth, you're actually falling. But you're falling in such a way that you never hit the ground. You just go around and you keep free falling forever. Remember when I talked about in my other video, if the Earth was transparent, you would do a kind of orbit where you just free fall continually? Well, yeah, an orbit is another kind of those, the traditional one. Antimatter is crazy, and we don't even know how it reacts to a gravitational field. For example, we don't know if antimatter falls like we do, normal matter, in a gravitational field, or if in Earth's gravitational field, it goes upwards. Why don't we know? Well, the mass of a positron is about 9 times 10 to the minus 31 kilograms. The mass of the Earth is 10 to the 24. To get the force, you have to multiply those two together. And you get something that you could measure on the order of 10 to the minus 3. But remember, we have to multiply by Newton's gravitational constant, which is tiny. So in the end, we get something on order of 10 to the minus 15. Our instruments aren't sensitive enough to measure that, so we still don't know which way antimatter goes in a gravitational field. In addition to traditional photons, the sun also produces tons of radiation in the form of charged particles. Typically, they're electrons and protons, and it's called the solar wind. Basically, what happens is these particles get trapped in the magnetic fields generated by the sun, and it works like a supergiant particle accelerator, where these particles just get accelerated faster and faster, and they reach enormous temperatures because they heat up the surrounding atmosphere of the sun. But what happens is the magnetic field lines produced in these areas get crossed sometimes, and it spits out a huge number of these particles called coronal mass ejections. When these come towards Earth, it's a good thing that we have a magnetic field, because the magnetic field takes those charged particles and redirects them to the North Pole, where it interacts with atmospheric gas, creating the northern lights. When you're at the equator, do you move faster than if you're at the North or South Pole or anywhere in between? Yes. That's because the Earth is always spinning about a constant axis, and that axis is such that when you're on the equator, you go about 1,000 miles per hour as part of this spin. Whereas if you're on either pole, you're not really covering any distance, so you have no velocity in terms of the spin. Now, everybody on Earth, regardless of where you are, has a velocity from going around the sun, but that's regular angular momentum. With the Earth spinning, and it spins 24,000 miles in a day on the equator, so 1,000 miles per hour. That's another kind of angular momentum called spin angular momentum, and that's why you go faster at the equator.